Alright, so today we're going to be talking about the genetic algorithm portion of Snake. This video specifically is just going to be for the single snake version of the game. Later on, we'll add multiple snakes and things like that. As for the format of these videos, I'll probably just do a code overview at the end, so if you just want to see the final code and don't want to hear any of this exposition, just skip to maybe like a minute before the video ends. Additionally, I think it's better if I just record myself coding and then do a voiceover of that recording, because the recording or the video of me coding this portion of the project up took about an hour, which I feel like is a pretty unreasonable upload time. So I'm going to try and keep it under 20 minutes. So we'll just go through essentially the recording of me coding with this voiceover, and I'll speed up the recording of me coding. So that's kind of what we're looking at here. So if we just go ahead, the first thing that I noticed, there's actually a bug. So if you go to game on line 68, that should be a 1 and not a 0, because we're basically double checking if head I is less than 0. So as for the genetic algorithm, we're just going to go ahead and create a class that's a genetic agent. And here I'm just going to kind of talk about what a genetic agent is going to entail. So we're going to have some population, and it's going to be filled with brains. These brains, our hope is that they will play the game and then somehow get some score or value based on how well they did. So I'm just color coding the brains here just to make it a little bit easier to explain how this is going to work visually. So like I said, each brain is going to play the game. It's going to get a score. And then what we're going to do is we're going to take the top 25% of scorers, which would be these two guys here, and every other brain dies. These top two in this 8 example, or top 25%, are going to reproduce in 2 ways. The first way is they'll just bring a copy of themselves to the next generation, and then they'll also bring a mutated version. So you can see that that kind of main color is the copy, and then the slightly altered color is the mutation. And then we're also just going to fill the other 50% of the population with just random new spawns. And this will help us avoid kind of local minima. So you could imagine one of these brains that's very successful, all that it has to do to be selected to reproduce at first is be even mildly successful. I suspect that the first couple brains are only going to increase their snake length by 1. So they could start out as a very like unoptimal brain, and if we only let those reproduce rather than introducing these random new brains into the population, we could just get essentially stuck with brains that are only increasing the snake length by 1 or 2, and that's not what we want at all. So finally we go all the way down. We do this for a bunch of different generations, and we get a final population. And that's going to be the goal. So then the question is, how do we go about actually programming this, right? We want, first of all, a brain that can play the game. We want a population of brains that we can mutate and have evolve over time. So here I'm just going to set up this genetic player, and this genetic player class is just going to house the population. So here we just have a bunch of parameters. The number of generations is just generations. The number of trials is the number of games that each brain is going to play. The window size is going to be the how much of the board the brain can see, and the hidden size is just the size of the brain. The mutation chance is just the probability that a mutation is introduced when spawning a new generation, and the mutation size is just the magnitude that those mutations will occur at. So here, current brain, that's just going to be the brain that actually plays a game when we go to play it, and we're just going to update that each time we go to spawn a new game. So here we're creating the population, and we're going to need a function called generate brain size, or generate brain, which we're going to build next. And what I want to talk about now is what a brain is actually going to look like. So each brain, each of those circles in our population up above, is just going to be a list of matrices. So here I'm drawing a matrix by explicitly writing out its rows, right? Each row is W, U, all the way down at dot, 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 V. So that's one matrix. It's one layer of the brain. And in our case, we're going to use 3 layers of the brain. So we're going to have hidden layer 1, hidden layer 2, and then output layer. And the output layer is going to correspond to our final decision. So the question is, okay, we have these matrices, so how do they actually correspond to creating a decision? And that's what I'm going to talk about now. So we're given some input vector, right? This is going to be the brain's interpretation of the game state. We're going to take a snapshot of the game, vectorize it, and then we're going to essentially pass that vectorized interpretation through the brain. So, and the way that we're going to do it is we're just going to matrix multiply the input vector with the matrices at each layer. So all that's happening at each layer is just matrix multiplication. So input vector multiplies by layer 1, and that gives us a new vector, which is then multiplied by layer 2, which gives us a new vector, which is then multiplied by output layer, and then that output layer times that vector is just going to be the output of the network. So here we're just talking about the dot product, right? So this matrix multiplication, each of those nodes, W, U, and V, is a vector, and we can just dot product the input vector by those vectors, W, U, and V, and then that'll produce a new vector, which is going to be AW, AU, AV. And then eventually we're going to get some output from the output layer, and then we just take the output that had the largest value, and that's going to correspond to which move. So here, 3 had the largest value, so we're going to return moves 3. So now the question is, how do we actually go about doing that? So let's generate the brain, and again, each brain is just going to be a list of matrices. So we're going to just create those 3 matrices that we want, which is going to be hidden layer 1, hidden layer 2, and output size. And these are just going to be randomly initialized for values between 0 and 1. And this just helps keep the output of each layer standardized. We want the input vector to be between 0 and 1. We want all of the corresponding layers to also be between 0 and 1. So here I'm just updating the parameters of generate brain now that we kind of know how it's going to work, and then we just return the list of matrices. So here, this original list of matrices that I drew, this is what's returned by generate brain. And then we'll see how that dot product is going to work when we do the forward prop. So here we're going to do get move, and that, again, this is standard across all players. It takes in a board and a snake. And now we need some kind of input vector, which we'll talk about later, and then we're just going to grab each of our components, each of our matrices, from the brain. And now here we're going to do the forward pass. So again, just to go over the forward pass a little bit, each layer is going to produce a new input vector, which we just pass to the next layer. So layer 1 creates some output that we then hand to layer 2. And all that we do is we just propagate that via the dot product through the entire network. So hidden result 1, this is going to be the result of multiplying the input vector by the first matrix. And we're just doing that row-wise. So you can see here that we're multiplying, we're doing the NP dot, that's right here, NP dot. That's going to go by the input vector and hidden layer 1. And those are the things that are being multiplied together, and we're just doing it row-wise. That's why we're indexing by I. And then we have this activation function here, tanh. All that that's going to do, and if you're not familiar with tanh, just go ahead and graph it so that you kind of understand what's happening. But it just smushes all values between -1 and 1. And again, that helps us not have values that just blow up in our network, because that can be very problematic. We add this 1 onto the end of that list just for bias. So essentially what we're doing is that's just going to be 1 times some weight when we do the dot product, and that way that weight is always the same. So it's just a bias term, which is just a bias is just a weight that is not dependent on the input from the previous step. So now that we have our output result, we're just going to take the maximum index, which we can just pick up by numpy.argmax, and then we just return moves we just return moves of that index, because that's the highest valued index. So now we want to talk about how to actually get that input vector, and that's going to be process board here. So the x's are going to be, or the x's and the y's are going to be the position of the snake, essentially. So this input vector, we started out as all zeros, and now I'm going to talk about kind of what we're hoping to accomplish by having this. So right here, this is a board, and we'll just say that the snake head exists here, and we'll have the window size be 3. And now this is the input vector that we're hoping to generate, and this is the process that process board is going to go through. So it's going to map each element in a window size around the snake's head, and it's just going to take those values and put them in a single vector. And then that's going to be our actual input vector. So the way that we do that is just to iterate over the board around the snake's head. So I and j are going to index the window, and I, j, j are going to index the board. And you can see here I'm just creating a starting point that's just half the window size away from the snake head in both directions. So, and then we just go ahead and first we want to check if there's any out of bounds, because we know that the snake can't go out of bounds, so we probably would want that input vector component to be something negative if it's actually out of bounds. Food we know is good, so we would want it to be something positive, namely 1. And now else we're going to have the board will be empty in this case, so we just set it equal to 0. That's pretty neutral. And then otherwise, we know that the component that we're looking at is another snake. So that way we just set input vector equal to -1. And then same thing here, if we're displaying, we just want to print the window that the snake sees. This will just help us kind of visualize what's happening. And then input vector, we're now just going to flatten it, which I don't do here. But I go back, this is just a mistake, I go back and do it later. So, actually, wait, let me just go back so that you can see this function before it kind of ends so abruptly. Whoops. Yeah, so right here, it should be numpy array input vector dot flatten, and flatten is a function. I go back and change it later, but I just don't notice it here. So now we're going to move on to the actual reproduction and the kind of spawning new generation. So this is kind of what we were talking about in the beginning. So we're going to just have some list that's the top 25%, and then we're going to spawn a mutated version of each brain in the top 25, and we're going to spawn a direct copy of each brain that's in the top 25. So we go through here, and we're just going to first add the brain to our new pop, and then we add a mutated version of the brain to our new population. And then we're just going to spawn the random copies for the other 50% of the population. So just self.generate brain, and it's the same parameters that we used in the init function. And then we just return new pop. So now we need to actually figure out how to mutate a brain. And the idea here is that we're going to create a copy. So each layer, each matrix, we're just going to create a copy of it. And then we're going to make small random perturbations to it. So we just iterate over the elements of this matrix, and with probability, so this if statement, it's just saying with probability self.mutate chance, add some small perturbation, which we'll see here. So that's going to be just some value between -1 and 1, scaled by mutation size. You can either make these very large, very small, and there are trade-offs for both. And then we just return the new brain that we've generated. So now one generation, this is just going to be one playthrough. So each brain in the population will play a game, and then we will just select those that reproduce. So here, scores is just going to house the scores for each brain, and then we just take the top 25% of that. So now here we're just creating the game. Outcome is just going to be whatever happens when we run the game, and here outcome, this should be play, not player, game.play. This is just a typo. I end up fixing it later. And then if outcome is 0, we know that the snake made it to max turns. And we want to print that out because it's kind of important to measure the success rate of our snake. And then here we're just printing out the max score that was attained by that particular generation. And we want to see how the max scores evolve over time. So here we get the indices of the top 25 brains, and we can just do that by np.argsort of the scores. And that will give us the indexes of the top 25 elements in that list. So and then top 25, and I reverse this list here, top 25, the bracket colon -1, that just reverses the list, and I do that just so that the best brain is always at the first index. That way when we are displaying the brains to see how they play, just the first one that pops up we suspect is the best. So now we just we just update the population, and then we're done with one generation, right? Because we played through, we updated it, and now we just changed the population. Now this is going to be evolve pop, which we're just going to go over num generations, and we're just going to do self.1 generation each time. And what that's going to do is just go through each single generation and update the population based off how well they perform. Here we're just going through and displaying the brains playing a game at the end. So a lot of the time when I do things that involve kind of a training and then an evaluation phase, if I'm visually evaluating it myself to make sure that things are going okay, I generally use this input function here, and that way I can just like run the training phase and leave my house, and then I come back and then just enter a key, like press any key, and then I get to see the evaluation. So here, this is going to just use a GUI to display what's going on. So here, I think at this point, I was just going through to make sure that everything was good. I mentioned a couple bugs earlier, but we'll look at me fixing those in a second. So here I'm just going to draw up the main function now. So I'm going to make a genetic player, which I always just copy paste the parameters and then just update them. I think it just kind of saves a lot of time. So here we're just going to run with pop size 100, number of generations 100 at first, and the number of games that each brain is going to play is just 1. That's going to be num trials. So now we're just going to, all that we have to do is just call genPlayer.evolvePop, and that should work. Here there are going to be a couple bugs. So again, the first one that I mentioned, it should be game.play. That's just a kind of a silly typo. Here we have another one. I forgot to pass the parameters of process board in line 45 of players. So we just want that to be the coordinates of the snake head and the second to last element of the snake. Excuse me. So run it one more time. There's still an error, and that just has to do with me not properly doing the bias. So here, output layer should not have a bias because it doesn't make any sense. Because we always want an output layer to always have 4 outputs, because that's how many moves we could possibly make. And then again here, that should be numpy.flatten. So now we run. I guess there's one more error. I think this is the last one. It really wouldn't be coding if you didn't have a lot of bugs. So, oh yeah, I left the one inside instead of having it outside. And then just a typo, and now we're good to go. The only thing now is that all the scores are 0, so I just need to actually add the score that each brain gets to the list of scores. So it happens somewhere around here. Yeah, here we go. So score equals length of the snake, I just never added that score to the list of scores. So I just have to do that, and now we should be working. So I'll show this first generation here just to kind of show how the snake can be kind of good, but not really. So we train it 100 times for a population of size 100. And now if you look, it's going to kind of go through, it eats two things, kills itself. And this one, it's going to do the same thing because it looks like it's very genetically similar to the previous snake. Yep, kills itself. This guy goes through a little bit and then kills itself in a different way. So you see it goes down, so it's very genetically similar to the previous snakes. Now I generate a few more. Let me just kind of skip through. Yeah, okay, here we go. So this trial is with number of generations at 500. And you can see that already at generation 200, we're already getting max scores of 13. So we're doing much, much better. So I'm going to go ahead and basically just speed through this. It might be the case that sometimes this video software is kind of weird if you speed it up too much. So yeah, you can see that kind of the max scores is going to change over time. So I'll just go ahead and jump forward a little bit. So now we're into the 300s. We see that we're already at 17. And then we just keep going. And now we're seeing that actually a lot of snakes are starting to make it to the last turn. They're surviving 100 turns and eating things. We finally got a snake that was able to eat 20. And now those genes we can really see starting to take over in scores. So I think we're getting pretty close to the end. You can see now, like, the scores are kind of just blowing past, mainly because there are so many printouts. But if you look closely, you can see a lot of 20s. So the snake has done, or the genetic pool has really done well for itself. And now we're testing, so I'll slow it down a little bit. And you can see over here on the left, this thing right here is the window. It's the input vector prior to being flattened. This is what the brain actually sees of the game. And you can see it's actually doing pretty well. It stays on the edges of the board. It doesn't go up to pick up this piece of food because it could potentially die. And this one, I think it makes it to length 20, but I do remember it killing itself. So kind of same thing. Like, I wonder if there are agents that go for this one here, and this one, and then turn right. There are probably a lot of variations that happen like that, and then just end up killing themselves. So the snake, we just saw that it kind of killed itself. So that is pretty much going to be the end for this. I'm going to do just a quick overview of the code, just to show you kind of how everything is at the end. And then we'll wrap this up. So here we just have players. Let me just zoom in a little bit just so that the quality is good. So here we have the init function. This just sets up all the parameters and the population. Here we have generate brain. This just generates a brain, and our population is made up of brains. And each brain is just a list of matrices. Get move is just going to do a forward prop of the network that's induced by the list of matrices. Process board, this is just the brain taking a snapshot of the current state of the game and turning it into a one-dimensional input vector. Reproduce just selects the top 25 brains, makes a copy of each of them, makes a mutated copy of each of them, and then spawns another 50% just random brains for the population. Mutate makes small perturbations probabilistically to each brain. One generation just does exactly that. It just runs one generation and then updates the population. Evolve pop just does all the generations. So for I and range dump generations, it just does all of them. And then at the end, we have this nice little feature that allows us to just visualize the snake playing games. So again, if you guys have any questions or you're having any problems with your code, feel free to ask. And if you have any comments about the video quality, style, anything, please let me know.